Thank you for the introduction and sorry for the small problem. So today I'm going to talk about the failure of nonlinear microstructured solids by cohesive and contact instabilities. So the given presentation is structured as follows. First of all, I'm going to talk about some motivations behind our works, and then I'm going to introduce the theoretical setting of the microstructural failure problem due to instability and bifurcation for a periodic composite materials, as well as the proposed interface formulations. After that, I'm going to show you some numerical results with application, and then I'm going to draw some conclusion and further perspective. So first of all, let's go with the motivation that are behind our work. As we know, the prediction of microstructural failure problem, a failure phenomenon in composite materials is a fundamental issue nowadays in nonlinear solid mechanics, due to the fact that with advanced technologies, this kind of material can be tailored to obtain enhanced properties, and thus to apply them to a different kind of applications that involve also large deformations. Moreover, we know that there are a lot of failure mechanisms such as fracture, decohesion, and instability. So attention must be paid to all of them and to their interaction between each other. So, as I said, it is fundamental to predict such failure behavior. And in the last decades, in order to address all these failure mechanisms at multiple scales in a very computational efficiency way, nonlinear homogenization scheme and multi-scale techniques proposed in a finite deformation framework have been developed. So our work presents an innovative nonlinear homogenization-based theoretical framework for characterizing the failure behavior of periodic reinforced hyperelastic composites induced by a reinforcement matrix decohesion and the interaction between the contact mechanism and the microscopic instabilities. So let's move with the theoretical setting of the microstructural failure problem. We define a representative volume element that occupies the domain, the region, the domain VE in that deformity configuration that contains internal contact and cohesive interfaces. So as we can see in the bottom part of this slide, the representative volume element can be made by a single unit cell or an assembly of unit cells in order to capture the microscopic instability phenomenon. After that, the ROE is driven along a macro-strain loading path by prescribing boundary conditions that depend on the macroscopic deformation gradient that is defined by the classical macro to macro coupling relations. As we all know, the microscopic deformation field can be split in a linear part and in a fluctuation part. So what kind of boundary condition we are going to impose? So we impose boundary conditions of periodic deformation that implies periodic fluctuation. And we impose antiperiodic tractions on the boundary of the ROE. And the solution will give us the macroscopic nominal stress tensor. As introduced, the representative volume element contains internal contact and cohesive interfaces, so a proper model is needed. Once a cohesive point pair is defined as a pair of material points that are in the same initial position, the displacement jump vector across the cohesive and contact surface can be decomposed into the normal and the tangential component vector, with reference to the current unit normal to the lower deformed cohesive surface configuration. And also the normal and tangential cohesive traction vector, referred always to the lower surface, are then defined. In this work, we adopted a reversible cohesive traction separation law first introduced by Tvergard in 1919 by adopting a full interface formulation for modeling both cohesive and contact interface phenomena. So, after the definition of the boundary condition that we are going to apply on the ROE and in what way we are going to model contact and cohesive interface, it's time to go ahead into the ROE equilibrium problem. So, at a generic contact pair that concern point in the same current position, we can define the two different equilibrium conditions, the global one that is represented by the equation 1, and the local one evaluated under frictionless assumption. The combination of the local and the global equilibrium condition shows that the nominal contact pressure on the upper surface is different from that we register on the lower one. And moreover, the nominal contact pressure can be obtained, as we can see in this equation, by an algebraic combination of both normal component of the traction and the normal component of the cohesive traction vectors. So our goal is to study the load-induced instabilities in periodic composite material that contain internal contact and cohesive interfaces. So as I'm going to show you in the next few slides, we're going to solve an incremental problem. So alongside the finite formulation, we need the rate RV. So at the generic contact pair, we can give the rate contact condition that includes the non-penetration condition. That implies that the nominal contact pressure is only active upon contact. And the additional condition for rating contact, that means that the nominal contact pressure then vanishes. Then at the same time, the rate equilibrium condition of the cohesive contact interface can be obtained by an asymptotic expansion of the global and the local equilibrium condition that I've shown in the previous slide. Regarding instead the rate version of the cohesive law that is obtained as follows, as reported in the slide. And it's important to pay attention to the analogy with the infinitesimal theory, because in this case, also when normal displacement jump and its rate are vanishing, the nominal cohesive rate traction is not necessarily purely tangential, because it has the normal component that must be calculated. After that, the contact cohesive formulations have been developed. Here we can discuss about the stability condition of the equilibrium configuration. So, sorry for that. So, considering a small perturbation of the current equilibrium configuration for a fixed macro deformation gradient, we can integrate the theorem power expanded identity over the time interval that goes from 0 to the parameter tau, and we can obtain the work of the perturbation force that I'm going to highlight in blue on this slide. And we can see that it is the difference between the internal deformation work and the work done by the antiperiodic surface traction, the nominal contact reaction, and the cohesive interface tractions, as we can see here. The positivity of these terms implies that additional energy must be provided by the external environment, and also ensure the stability, since the kinetic energy is always positive. After that, we can define the stability function over the set of admissible fluctuation rates, and its positivity ensures the stability of the current equilibrium condition. We can see here the stability function and the contact and the cohesive contribution. But the question is, how we can be defined the primary stability mode? So the primary stability mode is detected at the critical load parameter, where the minimum eigenvalue associated to the stability function first vanishes. After the exact formulation that I presented in the previous slide, we propose also two different simplified versions of the stability function. And the first one can be obtained by neglecting the term that is associated to the relative surface deformations, while the second one can be obtained also neglecting the term associated to the surface rotation of the contact cohesive interfaces. There are two simplifications that we can find in the technical literature, for example. So after that, now it's time to go ahead into the numerical results and to apply the theoretical dissertation to study the microbuckling phenomena inducing the bonding in highly deformable 2D layered composites. And the numerical results are going to illustrate how the way in which the bonding in conjunction with the fiber microbuckling may influence the critical load of the examined composite solid. The layered RV that we're going to analyze consists of reinforcing materials and at two matrix phases, and then we can see the embedded cohesive interfaces highlighted in red. The mechanical behavior of the microconstituent is then described by an hyperelastic constitutive law, but in particular a Newtonian strain energy density function has been adopted. Here we can see also the parameter in terms of Young modulus and the cohesive parameters required from the cohesive traction separation law that have been used. The numerical investigation consists of a parametric analysis varying some parameters such as the reinforcement volume fraction, the Young modulus Stiffer ratio that represents the ratio between the Young modulus of the matrix and of the reinforcement that we indicate with Ke, and the percentage of the integrity of the cohesive interface. But what does this term mean? This term means that when we talk about the percent of integrity of the cohesive interface, it means the displacement jump that is still available for the cohesive traction separation law. After that, the numerical determination of the critical load levels and the associated mode shape has been carried out by means of a one-way coupled parametric finite element model that has been formulated by a total Lagrangian approach. And it is made of two different steps, as we can see in the central part of the slide in the, I could say, framework of the proposed model. The first step is needed to evaluate the principal path step of the unit cell, while the second one performs in a sequentially way nonlinear eigenmode analysis and incremental boundary values problem. To this end, a proper code has been developed into the software console multiphysics. And as I said, in this part, we can see the flow of our proposed approach. Let's go now on the numerical results. Here, we can see the load factor that is plotted against the percentage of integrity, starting from a volume fraction equal to 0.05 to a volume fraction equal to 0.2. And we have different curves into the graph. The black one that represents the result in terms of macroscopic analysis, and the three curves that represent the results obtained by the exact stability function and the two simplified, called as simplified 1 and simplified 2. Why the dotted curve that we can see here represents the percentage variation of the critical load factors for the simplified formulation with respect to the exact one. Here a parameter Ke equal to 1 has been analyzed. So as I said previously, this parameter represents the ratio between the Young modulus of two materials. So going with a parameter equal to 1, it means that we are going to analyze an homogeneous materials. And we can see some interesting results. Generally, the trend is that the load critical factor decrease as the volume fraction increase. But we can see that in a range of the percents of integrity between 10 to 3 in this region, we can see that for a volume fraction equal to 0.05, we have a transition to a long wavelength of the critical mode shape. While for a higher volume fraction equal to 0.2, the stability always exhibits a long, the instability always exhibits a long wavelength. After that, we decided to vary this parameter Ke to a value equal to 2 and a value equal to 10, always analyzing three different volume fractions from 0.05 to 0.2. We can see that the general trend is almost the same to the homogeneous materials, but we can see some interesting results. For a value of Ke equal to 1, we can see that the maximum underestimation is represented for the higher volume fraction, for the volume fraction equal to 0.2, while for Ke equal to 10, the maximum underestimation regarding the difference, would say the variation from the simplified formulations to the exact one is detected for a volume fraction equal to 0.05. So we can conclude that high value of Ke lead to a strong reduction in the percent variation for the simplified formulations, and indicate that higher stiffness ratio reduced the stabilizing effect of the nonlinear contribution that have been introduced that arise at the cohesive interface. So in conclusion, we proposed a nonlinear homogenization framework that is going to use to analyze the failure behavior of periodic elastic composites. And The aim is to understand the nonlinear effect induced by the reinforcement matrix equation and the interaction with contact mechanisms and microscopic instabilities. So we introduce a stability functional and two simplified formulations for that stability function, and then we applied the two to investigate some numerical results on a 2D layered composites varying different parameters like the volume fraction, the Young model stiffness ratio, and the percent of integrity of the cohesive interfaces. So a future perspective, this model can be generalized, for example, in a dynamic context to analyze the influence of interfacial debonding on the incremental wave propagation properties. Thank you for your attention.